So in this lesson, we're going to look at gravity in a little bit more detail. And gravity, the way we've kind of defined it so far, is the weight of an object, which is its mass times the acceleration of gravity. 9.8 is the force due to gravity. This works very well for objects that are pretty close to the surface of the Earth and that are on Earth. But gravity works in other locations too. In fact, gravity is what we call a force at a distance. The gravitational pull of the Earth can be exerted on objects far away from the Earth. A good example is an object like the Moon, which is about 240,000 miles away from the Earth. Well, gravity is the force that holds the Moon in orbit around the Earth. Pretty much every artificial satellite we've put into space, gravity is the force that holds those satellites in orbit. If we look at the orbits of the planets around the Sun, ultimately it's gravity which is holding the planets in their orbits around the Sun. So Isaac Newton is the first one to really mathematically start to begin to relate gravity, this force, to other variables. He related it to the mass of the objects and the distance between them squared. Now this ultimately comes out of work done by a astronomer named Johannes Kepler, who was a little bit before Isaac Newton, looking at the orbits of planets around the Sun. So gravity acts between all massive objects. So if you have two objects with mass, gravity acts between them, and gravity is always an attractive force. Now, why gravity always acts between all massive objects, or why gravity is always an attractive force, we don't have good answers for those questions right now. We just know that that is true. And the relationship to calculate the force of gravity between two massive objects is this equation here. Negative capital G, which is the universal gravitational constant, times the masses of the two objects, the product of their masses, divided by the distance between those objects squared. The one thing to point out about the universal gravitational constant, 6.67 times 10 to the negative 11th, is that it's a very small number. And in fact, this force, generally speaking, is relatively small compared to the other fundamental forces. Another fundamental force with an equation looks very similar to this is the electrical force, the force exerted between two electrical charges, either the attractive or repulsive force. It has a very similar equation where it's divided by distance squared, magnitudes of charge multiplied by one another. This constant that fills in the spot of G is times 10 to the negative, or times 10 to the ninth. It is 10 to the 20th times bigger than this constant here for the universal constant of gravity. So me sitting in this room and you sitting wherever you are right now, there is a force of gravity acting between us. It's just a really, really, really tiny force. So let's kind of look at a situation like the one I have here. On the International Space Station, or really any other spaceship or object in orbit around Earth, if you're an astronaut sitting on that object, you experience the feeling of weightlessness. You can float around your environment and, not experience weight. Why is this? Clearly we could say that that's because gravity must not be all that strong. There's gravitational pull obviously between you and the International Space Station, but if we go back and look at this equation, your mass, the International Space Station's mass, are relatively small compared to times 10 to the negative 11th. So that's going to be a pretty small gravitational force. So maybe R is big enough between you and the Earth that that gravitational force becomes small enough that you don't feel it anymore. So let's do a quick calculation. So what I've done is I've taken myself as an example, 65 kilograms, and I wanted to figure out what is the force that I experience due to gravity pulling me around Earth at the International Space Station. So a few of these variables, here's the mass of the Earth, 5.97 times 10 to the 24th kilograms. Of course, the Earth is a gigantic object compared to me. 6.37 times 10 to the 6th meters, that is the radius of the Earth, and 4.01 times 10 to the 5th meters, that is the distance that the International Space Station is above the Earth. So in order to figure out, well, what's the radius, I want to know what is the sum of these two numbers. Usually when we talk about universal force of gravitation from the Earth, you want to know how far you are away from the center of the Earth. So if I calculate this out, I get 565 newtons. If I calculated my weight here on Earth, 637 newtons. So yeah, gravity is a little bit smaller sitting at the International Space Station, but not by as much as one would think. It's only about 10% smaller than the International Space Station. So my question is, wait a second, this answer here, clearly gravity must not be very strong at the International Space Station. That's not true. The gravitational attraction between me and the Earth is still relatively strong. 90% of what it is of me standing here on the Earth. So what is going on? Well, remember back to our elevator problem when we talked about normal force and that your perception of weight is really more about how other objects are pushing against you. Well, on the International Space Station, there's no normal force. Those forces don't exist, or they exist in different ways. Because the International Space Station is accelerating at the same rate you're accelerating, this would be very similar to you standing in an elevator and completely cutting the cable and falling down toward the bottom of the elevator shaft. You're going to experience weightlessness in that case. If the object you're sitting on or standing on is also in free fall, also falling under the influence of gravity, you experience weightlessness. There will be no normal force because that object is also accelerating as well with that same acceleration. You're in what's called a non-inertial reference frame. That's a very strange situation. You could also experience this if you're in like a bus or something and you drive off a cliff. During the time you're falling, you're going to experience weightlessness. That the bus and you are going to be accelerating with the same acceleration, and therefore the bus will apply no normal force on you. So that's actually a really strange idea and how weightlessness really works. The one thing to point out is that weightlessness is not the absence of the gravitational force. The gravitational force is still there. In fact, at the distance the International Space Station is still relatively strong. It just has to do with the fact that the International Space Station is accelerating with the same acceleration you're experiencing and therefore does not apply a normal force on you. If you want to talk about this more, I can give you a lot more examples of this where this comes into play. One thing to point out about Newton's law of gravity, keep this equation in the back of your mind. We will see this equation a couple more times as we work through various other scenarios, particularly when we get to looking at circular motion, because the uniform circular orbit is a great example of circular motion.